Hey guys, I have a midterm tomorrow, and I decided that a way that I'm going to try and do this is a class that I don't need to study a ton for because it's a lot of in-class stuff and learning, and I feel like I've actually retained a lot of the information that I've gotten from this class. And so I decided I'm going to speak everything out loud and explain everything, well not everything, but a lot of the basic concepts, and make a video out of it. I also just scooted across campus, so that's why I'm like sweating. Alright, so let's get started. So this is the class SCES 121, which is like science for people who are going to be school teachers. So the first thing we started talking about was magnets. Well, more specifically, we've been talking about models. So a model is something that represents something or like some interaction or relationship. It uses the familiar to explain the unfamiliar. The first thing we started doing in class was that we took a bunch of things and a magnet and saw if the stuff stuck to the magnet. And so paper clips attracted, wood block did not attract, like all these random things. And then we talked about how the different poles of the magnet and how there's the south pole and the north pole and how the middle is the weakest part and the ends are the strongest where the poles are, and that the positives repel each other and the negatives repel each other, but the positive and the negative attract. We started messing with a compass, and a compass is actually a little teeny tiny bar magnet like the arrow, and the arrow has the north side on it. That's the north pole of the thing. And so when you put a compass down, like normally it will point to the north, but funnily enough, not because like the North Pole has the North Pole. The North Pole like location actually is the South Pole of the Earth's magnet. And so the north side of the compass will attract to that South Pole. Compass, a little tiny bar magnet. So let's go to some of the quizzes now. First question on the quiz was, what is our cell phone policy for this class? It is off or on airplane mode. I got that wrong. So cell phones actually in class, and computers too, have been proven that if someone has it out, and like say someone in front of you is typing their notes on their laptop, that's actually a distraction for you. So it's not just a distraction. And like you may have like a Facebook thing that's giving you notifications. It's a distraction for you and for others. So don't do that. As a professional courtesy, what are you expected to do if you miss class for any reason? Email the professor and catch up on the work on your own time. Yeah, this class was a lot of in-class stuff, so if you missed it, you missed a lot of stuff. According to what we learned in class, what do magnets stick to? Some metals, but not all. So we also talked about how no model is ever wrong because it's representing different things for different people to learn about. So like say you show a kid like the solar system and have the Earth in the middle and the sun going around it, and say you have another model where it's the sun in the middle and the Earth going around it. They both show different perspectives, because for a little kid, he's like, oh, that makes sense why the sun will go like disappear. And then for like how it actually is the other way. And so it just represents different things. So it's never a like wrong model. It's just some are more scientifically accurate, but they both, the point of a model is to represent something and to explain something explain using something familiar so that they better understand the unfamiliar. Will you take a lot of quizzes in this class? Because they show the student what they actually know. That is a very important thing, and I believe it now because it really has been impacting me. Ooh, working memory. Each person has their working memory, which is kind of what you can be working on all at once, so you can be multitasking and well, not really. Multitasking is really bad for you. All right, I'm going to tell you a phone number. So 275-8394. Now, can you remember it all? Say it out loud if you can. Now add up all those numbers. Oh, wait. So you were able to do the first two. You were like, oh yeah, I got that. And then you were maybe able to do the second two, yeah. But then those numbers were taking up parts of your working memory. And so like you noticed as you got farther on, it got a lot harder. And if you weren't writing anything down or anything, it's a lot harder to do it because your working memory isn't capable of holding more than 4 things. Also for like little kids, it's 2. They only have 2 working memory slots. And then funnily enough, The group of people that have the least amount of working memories is middle schoolers, and they only have one. You can only tell them to do one thing at a time. So like if you have a bunch of instructions for people and they have to do it all at once, but it's all, or they have to like do it in order, but it's not written down or anything, they'll probably have a harder time remembering all the steps and doing them all. So there's long term, which is permanent, and it's like it has no limit. It's all of your memories and stuff. And that is what determines your IQ. Your short term is just kind of what you remember, like the phone number and like little things. So when you're remembering stuff, or even when you're thinking and trying to figure something out, that's usually your like little brain searching through your memories to try and figure out a way to do it, or like the correct answer for it. Working memory is what you use to manipulate the short and long-term memories. And the short term is more of just where you store the temporary information. You also have about 7 short-term memory slots. That's why you could remember the phone number. But then, like, if I read out a social security number, it would be harder for you to remember all of them because that's more than 7. Like, we did this in class and it freaked me out. I was like, wow, you're right. So I'll read this about models. All the different models show different parts of the picture and are different levels of understanding. So when we do all of them, we develop the whole picture and a better full understanding. And it also, as teachers, can help you show your students a way of understanding in their way. Like a kid's not gonna understand how an atom works, but you can maybe use a model to explain it in a way that they would understand, even if they don't understand all of the functions of an atom. Now I'm going to explain to you what Squiddy was. Squiddy was this little, I don't even know what it is. It's like a squeeze bottle type thing. Not a squeeze bottle, like a Biffit or something. Whatever, it was a little like round thing with the shooting thing that like a dropper kind of. And it had a little fishing lure on it, so it kind of looked like a squid. It was in this 2 liter of water, which had a little bit of air at the top. We had to basically talk about water pressure and how if you squeeze the bottle, it would go down, and if you unsqueezed, it would go back up. And it's because the air pressure, you could actually barely see it on ours. There was like a crack in the Squiddy thing, and so you could actually see the air getting closer together because the air pressure was increasing inside Squiddy. And so no air was coming out of it, but you could tell that the air pressure was increasing when you squeezed it because the air would get closer together so that more water could rush in there, because air is less dense than water. I don't know if that's true. Air can take up less, or air squeezes into less space when needed. Also, back to that model before about the Earth and sun thing, a kid is not going to understand that they are spinning at like super fast, like thousands of miles per hour. I don't actually know how much it is. This is how fast it's going. But kids not going to be able to fathom kind of the thought of, I'm not spinning that fast. Like, I would be able to feel it, but because the Earth, it's so big and it's just spinning all the time. But kids won't necessarily understand that way. And so sometimes you just got to use models to understand. So next we started talking about circuits. So like, light bulb with the little battery. And so you got to have the battery right here. And say this is the light bulb, and you got to have one part connected to the side, one part connected to the bottom, and then it would light. And we talked a lot about the differences between a circuit and a series. A series and parallel circuit. And so first off, we kept drawing a bunch of different models. So we kept drawing a bunch of different models of like how light bulbs actually work. And we had to determine that like it wasn't 2 sides coming in, because if you attached one battery and if you attached 2 different batteries, one on the positive side, one on the negative side, it still wouldn't light. And so we had to like prove that it was a circuit. Basically talked about how if you have 2 light bulbs in a row, so battery, light bulb, another wire to another light bulb, wire to the battery, that's a series. And so then they'd both be equally dim. But if you have it where it's battery, wire, so there's like a wire like this, and then you have a wire going to part of the light bulb and another wire going back on this side going to the bulb, and then another one just like that, it would be parallel, and so they both be just as bright. The reason why this is because they both have electrons going through them really fast. They don't have to go through, so they're only going through one. They don't have to go through two light bulbs. And we also talked about how switches worked. You know how there'll sometimes be rooms where there's a light switch on both sides of the room? And so basically how that works, I'll show you a picture. So basically how that works is that there are two switches, and the only time that the light bulb is on is if they're both one way or both the other way. And so whenever one of them is off, then it doesn't work out and it's not on. So the speed of the current in a series circuit, it actually is slower because it just has more obstacles to go through. Like imagine a guy, so you're in a classroom, there are a bunch of tables, fire alarm goes off. It's going to be much easier for him to run out of an empty room than it is for him to run out of a room with a ton of tables in the way. See how it's kind of like that, and how the electrons have a lot less obstacles when there's no light bulb, but with the light bulbs, they're kind of like the tables. We also specifically talked about how all of the electrons get back into the battery. It's like a path. They don't ever like get burned up on the way, because that's not how it works. Okay, so what is the correct way to classify electric circuits? And there's no correct way to classify anything. So what is the problem with saying that one of the differences between living and non-living things is that all living things can reproduce? So some living things can only reproduce at certain times. So like a baby can't reproduce, and like a really, really old person can't reproduce. It's only for a certain amount of time. It's like if they stop being able to do that. And also there are people that can't reproduce, and that doesn't make them not living. So this is kind of about classification. So why does a third grade student say that human is not an animal, while a college age student says that a human is an animal? It's because third graders may have a different way of classifying animals. For example, they probably don't think of an ant as an animal, but they definitely think of a dog as an animal. So they kind of classify it in different ways. But if you ask a college student, is an ant an animal, they say yes, because they know the different kingdoms and stuff. And they both are just classifying them in different ways. It's kind of like how some people classify hot dogs as sandwiches and some people don't, and it's just based on different information. Why do humans classify things? It's to help us better understand and make connections with objects and like see the similarities. So like there may be a rock that is very hard but actually has a lot of the characteristics and similarities to a really soft rock. So it really it's a way to better understand and connect things. We did this experiment with crayons and it splattered all over my notes. So let's talk about that experiment first. So first we shaved a bunch of crayons on like cheese graters and like zesting stuff, and then we made a big pile, and then we wrapped them in tinfoil and smushed them all down, and then we opened it back up, and it was kind of hard, or not hard, but it was like soft and in a rock form. And that is seen as a sedimentary rock, because a sedimentary rock is a bunch of sediments from rocks all getting pushed together, and it's only done through pressure. So the next thing we did with our crayons is we took our crayons and put them back in the tinfoil thing and dipped it into a thing of warm water for a little bit, and then took it back out, and we opened it back up, and it was partially melted and more cemented together, but you could still see individual colors and stuff like that. And so that's kind of the metamorphic rock. So that takes pressure and heat to kind of make it, but it's not fully melted and cooled together as one. Because the next thing we did was we went and got a hot plate, and then, as you can see from my notes that are covered in little crayon things, we took the crayon thing in aluminum foil, and we melted it on a hot plate, and then we poured it into a thing, and that's how, and that became it became a crayon thing that was all one color and kind of solid and in a big form. I don't know. And that's kind of how indigenous rocks are made. Indigenous is not indigenous. Igneous. And that's how igneous rocks are made too. they get so hot and then they all melt together and then they fully heal. Well, it goes heat, melt, cool, solidify. So I also have this cool drawing little thing. For all of the other rocks, to make a sedimentary rock, they have to be ground up again and put back into sediments. And so they could be made into a sedimentary rock. And then a sedimentary rock, if it goes through magma, it can melt into an indigenous rock if it's all melted together. And then also, if it's like slightly melted, it can turn into, oh dang, it can turn into a metamorphic. Also, a metamorphic can go into magma and become an igneous. And then igneous can go back to sediments and metamorphic back to sediments. Also, sedimentary rocks can be put back to sediments too. So how are metamorphic rocks made? Heat and pressure. What do you call the very small bits of rock, plant, and animals that can get squeezed together at the bottom of the lake? Animals? To form a rock. That's sediments. I spelled it wrong and they fixed it. I spelled it with an E. Well, I spelled it with 2 E's. No, 3 E's. What classification of rock will both lava and magma become once they turn into a rock that is igneous? Igneous, not indigenous. How are igneous rocks made? Heated, fully melted, cooled, and then solidified. What are 2 different things you might look for if you want to determine if a rock is sedimentary? So there are many different types of rock in the rock. Like you'll see little pieces of all different rocks. It also has a rougher feel to it. It's not smooth. And it can also be more fragile than the other types of rocks. Describe the steps or the process that must occur to turn an igneous rock into a sedimentary rock. So the igneous rock has to break down into little sediments, and then it has to have applied pressure. And then you have sedimentary rock. So we base it on how they were formed. So either pressure, heat and pressure, just heat, how they were formed is how we classify them. How many rocks cannot be changed into a sedimentary rock? None, because all rocks can do that because they can all go back to sediments. We did this experiment where we got a tub and we filled it with room temperature water. And then we had these little jars full of, this one had hot water in it and we put blue food coloring in it. And then this one had red food coloring in it, and it was cold water. It was like ice water, but without ice in it. That's important too. And we poked 2 holes in it, and you could see that the blue hot water went to the top, and the red cold water went to the bottom. And so one of the reasons why he did it as blue and red, like switched them of how we usually think, is because actually, like think of hot fires, they're actually like the blue is the hot part. And so he just wanted to get rid of that bias in our heads. So the hot water rose to the top because it was a lot less dense and it was bouncing around. And so it went to the top. And so it was like mid-density in the middle with the room temperature water. But then it was decently dense, decently dense. It was very dense down at the bottom with the cold water because they weren't bouncing around as much. They were more stuck together. So the red color came out of the bottom slowly, but the blue, like at the top with the hot water, came kind of fast out of the top hole. Warm water is less dense than cold water. Hot water will rise and move more quickly, and the cold water will sink and move more slowly. So the next thing that we did was we took 2 beakers and we filled this one with warm water and this one with cold water. But this one had blue food coloring in it. And we stuck them on top of each other and then like with a paper in between, and then we pulled out the paper and they mixed a little bit in the middle, but they really stayed where they were because the less dense stuff was already on top and the more dense stuff was on the bottom. But then we did the same thing and flipped it, and it quickly trickled and kind of switched. It also mixed a lot more, but it was still like darker at the top slightly, but it mixed a lot more during that situation. Temperature is a factor in density, and the less dense, the higher the temp, and vice versa. Then the next thing that we did is we took a different bin, and it had little divots on the bottom, and we put cups under the divots, so 2 cold ones on each side, and then a hot cup in the middle, and we put a little drop of red in the middle, and we watched as it drifted up and around the edges and back. So basically made a circle. And we were talking a lot about currents. So it was pushing up because it was less dense because it was being heated by the hot cup underneath it, which was pulling in the water, because it wasn't just going to have empty space. So it was pulling in the water from the sides. And so then that would get heated and move up. So it basically made a current, just like we have in the oceans. So then we also, like the first thing we did when we started doing this is we took a cup and we put a piece of paper towel in it, like we taped it in there. And he was like, all right, guys, you got to get it not wet. And so, like, the genius that I am, I was like, guys, we just got to put it upside down and make sure that no water gets in it because the air will fill up the space. So we did it. Our paper towel wasn't wet. We were all good. And so why won't the water go into a cup if a cup is held upside down underwater? And it's because the air has nowhere to go and it's taking up space inside the cup. So the next thing that we did is we poked a little hole in the top of the cup. And immediately when we put it down, the cup filled with water because all the air could escape. And so the water could take up that space. Also, something that we've been talking about a lot is, does heat rise? And no, it does not, because heat is a concept. Heat is like happiness. It's not a specific thing. Things that are warm and less dense will rise, but that heat is not a specific thing that is rising. Like hot air will rise, but not heat. Heat is a concept. So consider the gas of water vapor. What will happen to the particles making up the gas when the gas becomes cooler? The individual particles just get closer together. They'll just little penguin huddle all together. So another experiment that we did is the classic, like, get a bottle and then you put vinegar in the bottom and put baking soda in a balloon, and then you lift and attach the balloon to the top of the bottle, and then you lift up and let the baking soda fall, and then, oh my goodness, it starts to fill up with gas. The baking soda and vinegar were still both present and they were just bubbling a lot, and so there was no new substance in there. It was being created from the gas, or from the reaction. So another cool thing that we did is we took like a match, and we had a big tub, and we took a match, like held it in there, obviously it stayed lit, blew it out, and then we did this thing where we blew bubbles in it and they fell down. But then we took a bunch of vinegar and baking soda and poured it all in the bottom of the tub, and then we did the reaction, and then we did the same thing with the bubbles, and it was like floating right above the surface because the bubbles were lighter. The air inside most of the room was lighter than the gas that it had made, which was CO2. And so also then we like scooped up that gas in a little cup, had a little candle, and we like poured it on the candle, and it put the candle out because it's CO2. If anyone actually watches this and this isn't just for my studying this, I hope that you enjoyed it and that it helped you learn some things. Yeah. Pray for me in my midterm and my class grade overall after this. See you guys next time. Bye.